morning, everybody. Webinar 3 this year with our series focused on new energy, alternative energy, renewable energy. Just a reminder again that we have a chat option, we have a Q&A option. So in the chat, some general things, but please, for your questions, look at the Q&A button. And as the speakers are speaking, please, any questions are open, and our facilitator will look at the Q&A to try to answer all your questions, either in the Q&A or afterwards in the recording that we will send. We've had so many webinars last year and this year, slightly less this year, but please, you will see in our YouTube channel, you can have all the previous webinars available there. So if you're curious in some of the other things that we've been talking about, please check out our YouTube channel and look at the webinars and at the Q&A sessions that we've had. This year, we really focus on renewable energy. We've already had a webinar introducing this whole topic about the just energy transition. What does it mean for South Africa, and how does our landscape in South Africa looks like? We followed it up with a focus on concentrated solar power and thermal innovation, where we looked at large and small scale applications. We also looked at how to integrate that into the industry. So if you've missed it, please check it out and subscribe to our email list, where you will get reminders when we post things and when we plan the new webinar. You can also follow us on LinkedIn to see what OTC does. And Elsie has posted everything for us in the chat box for you to follow those links to make it very easy for you at the end of the day. Today, we go beyond the blades. Today, we focus on another resource that has powered humanity for centuries, the wind. The challenge isn't to find the wind, it's knowing what to do with it. Wind energy has become one of the fastest growing sources for electricity worldwide. Modern wind farms are larger, smarter, more efficient than ever, yet they raise important engineering, environmental, and societal questions. So today we're going to look at the fundamentals, how to convert moving air into power. We're going to look at the next generation technologies, and we're going to see how can we use technology to use the wind responsibly. I love this quote. The pessimist complains about the wind. The optimist expects it to change, but the realist or the engineer adjusts the sails. So let's see how we can adjust the sails today to harness the wind. Our first speaker for today is Rian van Schalkwyk. Rian is one of our principal consultants at OTC. Rian is a registered professional engineer, and he started with his degree in electronic engineering from Stellenbosch University. I like to say Rian is an all-rounder. He doesn't only stick to electronic, he actually expanded his capabilities to some electrical work as well. And he has such a vast range of industries that he worked in. He's really an all-rounder. Mining, mineral processing, pyrometallurgical facilities, arc furnaces, iron, steel, oil, gas, renewable energy. And he has held a different leadership roles as well across production, maintenance, major engineering projects, owner teams, consulting engineering. But he has a particular passion for renewable energy and how to integrate the sustainable energy solutions into industry. So he's really the full package that we are presenting with you today. Rian is going to talk about from wind energy to useful electric power. From wind energy to useful electric power, Rian van Schalkwyk. Thank you, Rian.
Oh, thank you, Wilmien. What a beautiful introduction. Good morning, everyone. As mentioned, I'm a consultant with OTC. And in this short presentation, I will talk on the basic of wind power generation. And I'll do it by addressing the following short questions. Why wind turbines? Is it relevant to South Africa? Engineering challenges to wind power. How do they work? The basics. And how does electricity get from the mountaintops to my house? In today's energy-hungry world, we are in dire need of additional energy sources. Wind turbines are a renewable energy source. The wind is still free. There's no fuel costs. There's also very low carbon emissions. It is highly scalable from large-scale utility wind farms to single turbines powering a single home. And as Wilmien said, worldwide, wind-generated electrical power is becoming one of the world's lowest cost energy sources. When we look at the South African landscape, from the South African Wind Atlas, we can see that despite popular belief, the windy areas are not just along the coast, they're also distributed inland. If we look at the next, which is a map of the South African wind farms, we can see that these farms are installed in the areas with a high annual wind speed. I'll move back to the previous one. There's the atlas, and there's a map of some of the installed wind farms currently. Is wind power relevant to South Africa? When you look at the estimated commercial operational wind farms in South Africa, there are currently 49 fully operational wind farms, with 13 or more in construction. The number of the wind turbines of these farms varies from just 7 for the smaller ones to 96 wind turbines per farm for the larger ones. The generation capacity of the wind turbines is also increasing. It started off with smaller 1.5 megawatt turbines, and currently 6.2 megawatt generating turbines is installed in the current installations. The total installed generation capacity of the wind farms varies from 21 megawatt to 155 megawatt per farm. Currently, the total generation capacity of these 49 wind farms is more than 5 gigawatt. This is roughly the generation capacity of a medium to large coal-fired power station. So from this, we can see that wind power generation in South Africa is well established and is growing. Some challenges with wind power. Intermittency. The wind does not always blow constantly at the same speed. When you look at the power grid, it also doesn't like fast wearing power sources. So integrating wind power with the national power grid can be problematic. This can be mitigated and managed by installing large battery storage. Although this is starting to happen, it is still very expensive to install this large battery storage. Also, to integrate wind and solar generated energy with a power grid, the demand and supply needs to be synchronized. Okay, for this requires accurate weather and wind forecasting. And as we all know, weather forecasting is not always an exact science. The transmission infrastructure. Spare capacity is required on existing power lines to transport the energy to the end users. If spare capacity is not available, additional energy sources cannot be added to the electrical grid. Maintenance. Wind turbines are mechanical machines. They do require maintenance throughout their lifespan. Wind turbines also need to be protected against very fast and strong storm winds, which can damage or even destroy wind turbines. Then there's also some environmental considerations. Erecting these huge wind turbines require large foundations with roads, infrastructure, and power lines, often installed along hills and mountains. Another concern can be that the tips of the wind turbines rotate at a very high speed, which can be detrimental to bird and bat life. An interesting presentation to follow will address this. When we look at the power curve of a typical small wind turbine, in this case it's a 10 kilowatt variable pitch downwind turbine, we see that the output is very non-linear, Wind power increases with the cube of the wind speed. For this turbine to generate the rated 10 kilowatt, a wind speed of more than 43 kilometers an hour is required. We can see that at the wind speed of 20 kilometers an hour, only 2.5 kilowatt of electricity will be generated. During storm wind conditions, the turbines must also be protected against damage. This is done by variable pitch rotors and brakes and other means. And we often found that small turbines that lacking these protection are often destroyed by storm winds. When you look at how do wind turbines work, the rotor blades are shaped like an aircraft wing. The lift causes the rotors to turn. The aerodynamic efficiency of the wind turbine is typically between 40 and 50%. When you look at the diagram of a typical wind turbine, we see that the rotor blades turn the main shaft. The gearbox and the generators are contained in the upper housing called the nacelle. The brake system, which is critical in protecting wind turbines against strong storm winds, is also mounted there. The power controller and transformer are typically mounted around the base of the wind turbine, from where electrical cable and power lines connect the wind turbine to the farm substations. Let's take a closer look at the energy conversion process. Wind energy is not electricity. It's a source of kinetic energy that must be converted through several engineering processes. The wind containing kinetic energy blows on the rotor blades, rotating the blades. The rotational force is transported via the gearbox to the generator. The gearbox also increases the rotational speed as required by the generator. The generator generates electrical power, typical at a low voltage, which is typical 400 to 690 volt. This power is fed to the power controller that regulates the power to the required voltage and frequency. A transformer then steps up the voltage to medium voltage. It's typical 11 to 33 kilovolt. The electrical power from all the turbines is transmitted by electrical power and power lines to the wind farm substation. This is also the connection point for the transmission grid. Now for the final question. How does the generated electricity get from the mountaintops to my house? As the wind farm substations, a step-up transformer increases the voltage to high voltage. Now this is above 220 kilovolt up to 765 kilovolt. That is used in the transmission lines. The higher voltage means a lower current. For lower power loss and thinner, the lines are cheaper. The electricity is transmitted by transmission lines through various transmission substations along the countrywide electrical grid. From the nearest transmission substation, power is transported via transmission lines to distribution substations. At distribution substations, the voltage is stepped down to medium voltage and is transported via power lines and electrical cable to the end users, being the residential areas, houses, commercial buildings, or heavy industries. In the residential areas, small transformers, often located inside mini substations, step down the voltage to low voltage. The houses are typically supplied by low voltage, which is 400 volt 3-phase or 230 volt single phase, which we use in our homes. And that, my friend, is how we can watch the Springboks beating the All Blacks in my TV, in my house, as long as the wind is turning some wind turbine somewhere in South Africa. Thank you.
Thank you, Rian. Normally, I would say for most people, it's a windy day, but for engineers, it's a potential power plant. But after that presentation, I must almost say for most people, it's wind, but for Rian, it's a rugby game to enable us to get the power to watch the rugby game. Lovely. Thank you, Rian, for sharing that. And that is a perfect introduction to what we want to share today about the wind energy. But let's see which direction the wind blows today before we go to our next speaker. Our next speaker is Dr. Gareth Erfort. I hope I pronounced your surname correctly. He is the lead wind engineer from EDF Renewables. Now, Gareth started with his PhD on vertical axis wind turbines at the University of Stellenbosch, and then his career took a long and windy road maybe, but a very interesting road. As he gets more industry exposure while he keeps on his academic career, it's interesting to see those two parts that he kept together the whole time. So he was the principal engineer at CSIR in their wind team, which formed part of the larger Energy Center Group. Even more hands-on experience where he worked for a consulting company, and then he joined the international IPP. Currently, he looks at wind engineering for the EDF Renewable South Africa, but he maintains close ties to academia with an adjunct associate professor appointment at Stellenbosch. His personal passions include offshore wind and small wind turbines. So Gareth, we are very, very curious to see what you're going to join with us today. Gareth is going to talk about the next generation of wind turbines. The Next Generation of Wind Turbines by Gareth Erfort. Thank you, Gareth.
Hey, good morning, everybody. Thank you very much, Wayne, for the introduction, and Rian for the interesting presentation, which segues quite nicely into what I will be presenting on. I don't claim to have a crystal ball, but these are trends that I have seen or that are pretty evident in the industry at the moment, both from industrial applications and academic studies. The biggest thing we talk about when we see turbines these days is their size. They just keep getting larger and larger. It makes sense that they get larger because the swept area is the main driver for how much energy we get out. So rotor diameters are increasing constantly, and if you go offshore, rotor diameters reach lengths that will dwarf anything you've seen onshore. So the current offshore rotor diameter size for reference cases, so for base case models, would be for a 15 megawatt Vestas 236, which is 236 refers to the rotor diameter. There are larger versions, such as the International Energy Agency's 22 megawatt rotor diameter of 284 meters. There is, however, a tipping point. It used to be go larger and produce more power, but there is a balance between rotor diameter and rated power. And when you see the orange line in the bottom right screen, let me get it the other way, on the bottom right, when the orange line passes the blue line, we are not getting more bang for our buck by getting larger and producing more power. So we're trying to get the right rotor size as well as the right power rating for each turbine that we develop. We also can't just keep getting larger because mass is actually scaling faster than the energy. The mass of our blades gets bigger and bigger by a cubic relationship, whereas we get speed or power out through a squared relationship. And at the moment, the biggest problem for turbines getting larger is the logistics. So if you were transporting, for example, with a rotor diameter of 284 meters, the blade is 150 is 300, so minus that, 140 something meters blade is tough to move around on land and easier offshore, but you still have to get the blade to the right location offshore. So you have a staging area at a port, and not all ports can even handle those kind of blades. You also have issues with the size of the blades having more erosion at the tips, and the aerodynamics become hard and hard to control. So when I talk about the blade tips, we have to consider how the blades are designed. They in themselves are a marvel of engineering. At the moment, they're made of laminates. So you have different materials coming together to supplement the blade shape and design. At the leading edge, we have carbon fiber spar caps so that you have stronger front edge, so reducing the erosion you get in the front. We have Glass fiber layups to provide the strengthening, and the spars are now no longer wood, but they're replaced by PET foam. So these are to make it as light as possible, as strong as possible, and as tough as possible. The blades themselves also must be able to twist. So there is some bend allowed in a blade design, and the aerodynamics change from the tip to the hub. So you have the change in blade length, which needs to be accommodated. The resin systems are also very far advanced because these blades are made of laminates, and we know that carbon fiber and these kinds of designs are hard to recycle. So we try to develop resins that allow you for easy recycling, so you can take the fibers out and reuse them. There's the Zebra project at the moment, which is a zero emission blade developed in Europe, and it is currently in production and is used in farms. All the onshore blades in South Africa right now don't have that option for recycling, so they are going to be chopped up and repurposed into a lower form of use. They don't necessarily end up in a landfill, but the future looks bright. Towers and foundations, if your blade is bigger, you need to get it higher off the ground, so we need longer towers. Tower heights at the moment stand at like 120 meters to 130 meters, nothing bigger than that onshore at the moment. Offshore starts much higher than that, and we'll discuss the offshore foundations later. Towers can be made of steel or concrete, but there are advances to use towers made of wood. Nothing in production, just test cases at the moment. Finally, if we look at the rest of the components, things like the generator, the part that actually generates the electricity, we're now moving towards permanent magnet machines, which makes it easier to, direct drive machines, which means we don't have a gearbox, so we have less failures. The direct drive machines are very large bulbous designs, so you won't see the long thin nacelle. You'll see a fat blunt-nosed nacelle, which instead has these two big magnets that rotate, that allow for rotation at a slower rotational speed, but develop the same amount of power. Other advances are not just on the mechanical side, but it's how the turbine interacts with the world around it. So we have serrated trailing edges. So these are actually designed not exclusively, but somewhat from whale fins, where the the serrated edges along a turbine blade create a noise reduction by displacing the air, so it doesn't propagate as far. So you can be closer to a turbine and hear less sounds. We have the sweep and design of blades is a lot more sophisticated these days, with modular rotors decoupled blade length from road and port constraints. So you can transport blades in pieces, so you don't have to worry about the full size. We have aeroelastic tailoring and bend twist coupling. So fiber placements that allow you to bend the blade even more, so you can allow for more flex. So you don't have to worry about those gusty wind conditions. You can have low induction rotors, so they operate below the bed's optimal axial induction. So we don't have as much power produced, for example, but we're able to get power in wind speeds that typically weren't taken advantage of before. And then we have LiDAR on the nacelle. So the LiDAR would look forward instead of looking upwards. Typical LiDARs look up to give you a wind profile. These LiDARs look in front of the turbine and tell it what wind is coming towards it, so that it can pitch and adjust its control as the wind approaches it, making it more effective at extracting wind. So with all these advances, turbines are not becoming generalized, they're becoming specialized. So each turbine can have a special role or a special place. You have low wind onshore turbines, you have high wind turbines that can survive typhoons, you have turbines that are fixed bottom, you have turbines that are floating, and you have turbines that need to be able to be upgraded. So they're past the 20-year lifespan, and now can you just adjust one or two items so that the farm can continue working? I want to talk about the bottom image first. This is the different designs you'll see for offshore wind turbines. So from the left to the right, we have fixed bottom all the way to floating. Fixed bottom are monopile or jackets, something that we've seen quite extensively in the offshore drilling. Semi-submersible spar and tension leg platforms. Those are the cutting edge where we're looking at depths greater than 100 meters. We can't touch the floor, but we can have these massive chains keeping us anchored in position. And everything below the waterline might vary, but the items on top, the turbines themselves, will be then standard. So that's what I see in the future for offshore wind and what is been happening in offshore wind. I wish passionately it comes to South Africa, but that's a different topic and a different webinar maybe. Let's go to the top. Drivetrain changes. I mentioned before, there's direct drives coming our way, medium speed or hybrid gearboxes, so two-stage gearboxes, which then have lower mass, magnet content. They have superconducting direct drives. That is a lot further forward. We have electrical changes. So when we go offshore, we actually like to use DC connections so that we can transport the energy onshore before we hit the AC side of things. The support structure I've mentioned before is all the images you see at the bottom between fixed bottom and floating. So the rated capacity and rotors, they are getting larger. Every time we talk about turbines offshore, every time we talk about turbines in the future, we see the megawatt sizes increase. Rian mentioned the onshore components of South Africa range from 1.5 to 6.2. 6.2 is the largest onshore wind turbine that we have installed in the country at the moment. It is definitely not going to stay that way for long. We do have the constraints, as mentioned before, about driving the blades to the location. If you look at the blades or the turbines available at the moment, the Halliday X is a 14 megawatt from GE. Siemens Gamesa has a 15 megawatt at 236 meter rotor diameter. Vestas has a 15 megawatt at 236 meters diameter. And Mingyang has a 18 megawatt. I can't tell you the blade went up 260 meters for that one. Mingyang, Goldwind, and Envision are Chinese manufacturers. Vestas, Siemens Gamesa, GE even have a European base. So they're definitely in the same range of power outputs. They're just being designed on different sides of the world. So when you talk about wind turbines, and Rian mentioned it, they are intermittent. We do know that they will be producing power when the wind blows, but I can't promise you the wind is going to blow tomorrow at a certain wind speed. And so when we talk about wind farms, we talk about something called the capacity factor, how much wind or how much hours in a 8,760 hour year have they been producing power at their full power. And capacity factors in good locations can be 30 to 40% onshore. I think, and I stand to be corrected if anybody knows better, turbines in South Africa across the REAP programs are tipping out just under 30% on average capacity factor. And in the future, we're looking at wind farms that can reach capacity factors between 50 and 60%. You can see that the onshore capacity factor for the US at the moment is around 40%. Our wind farms are typically spec'd for 20-year lifespan, thanks to the REAP contracts that they've signed, but now we're looking at 25 to 35-year design life, which means the turbines have to last longer and survive full operation. Turbines have a technical availability greater than 97%. At the moment, they're sitting at 97. We're looking at pushing that up. And if that availability is 97%, it means for 30 years of its life, it's only allowed to be down for 3% of that time, which is quite fantastic. The land footprint is around 34 hectares per megawatt. So during construction, you will take up a large space when you put the blades down and you put the tower up. But once the turbine is constructed, you don't see the foundation. Agriculture happens underneath the turbine. I've got some lovely images of sheep enjoying the shade of a turbine and chowing away at the grass underneath it without any complaints about the noise. And then finally, we have the LCOE, which is dropping fantastically. It's been dropping since REAP round 1, where the cost was greater than 2 Rand per kilowatt hour. It's now down to 40 cents in the last REAP round per kilowatt hour. And that is obviously what Eskom pays, sadly not what we pay. So yeah, these are the boundaries that are being pushed by the next design in wind turbines. Life cycle and circularity. So it was also mentioned that these are low carbon emission or zero carbon emission energy production systems. You can't say they're zero for exact reasons, because while they're being made, they are using carbon-intensive processes, the materials being mined or the materials being brought into construction. But with the current designs, you can pay back your energy usage. So within 12 months of a turbine operating, it can have you generate the same amount of energy that it was used to create it. And then after that, it is all free energy, no carbon emissions. I mentioned that blades, the Zebra project, is one of the biggest issues in terms of turbine recycling. But by mass, we can already do 85 to 90%, and that is, excuse me, mainly because of the tower and the nacelle and the other steel components. And as I said, the Zebra project has pushed the boundaries now where we can also recycle the blade. So that is getting a lot closer to 100% of use. The leading edge protection and LiDAR control helps extend the life of the blades, which means we don't have to replace them as often. The blades, apart from being recyclable, those that aren't recyclable have been repurposed. So there are some nice examples in Denmark where blades are being used as bus shelters. And then if we're not able to recycle the blade, we are able to recover pieces of it and use it in lower industrial applications. The other aspect to consider is how the blades or the turbines interact with the world around it, and that's in construction and operation. So a talk that will follow on from this one would be around the avifaunal interactions. But at the moment, advances in blade technology include just painting the blade black, and that has seen a reduction in bird fatalities. We are seeing a reduction in bat fatalities thanks to using the use of radar or optical devices for curtailment. So it sees the animals approaching and then it instructs the turbine to stop. We are dropping the acoustic emissions, so you can get close to turbines, they're not as noisy. As I mentioned, that's from serrated trailing edges. We are able to now use bubble curtains. So that might be something that doesn't come first to mind, but when you're building offshore, the piling activity is a major disturbance to the marine life, acoustically as well. It propagates many kilometers thanks to water. So what they now do is they create this bubble curtain around the area of construction so that the sound doesn't propagate. It also dampens to some extent the sediment that expands during the piling. So that's quite nice. Grid services, so we are now not just generating power, turbines are able to support the grid. They are not supposed to be islanded. They have to assist the grid in stabilizing in cases of frequency problems and other items that might happen on grid issues. Yeah, we're not perfect. There are still things to be discussed. Offshore effects on seabirds. We haven't done enough studies on the result of how these massive offshore turbines are affecting seabird life. The demand for magnets and rare earth materials is getting bigger and bigger every time. Leading edge erosion has been a topic throughout the slide deck. You can see that it degrades annual energy production by up to 5%. And because we are building larger turbines, and because we are building larger turbines in areas that are flat, namely the sea, we are seeing a lot more wake loss, which means I didn't get the energy I was promised, or that the turbine in front of me, upwind, is taking all the energy while I'm not seeing as much, and that reduces the efficacy of the wind farm. That's what the trends are showing us. This slide doesn't show us the trends. This shows us the academic side, the desires of wind farms going forward. We have things called airborne kites. There is an airborne kite which basically lofts the turbine into the air, so you don't have a tower. It's held up by a kite, and at a higher atmosphere or higher level above ground, the wind speeds are better. So you have this massive tether which then transports the energy down through a cable. You have the rigid wing version of this. This doesn't get held up in one position. Instead, it acts by like paragliders do. When you pull on the sails, it causes that oscillation motion, and the oscillating motion then pulls on a generator that is grounded. similar to the image you'll see on the right-hand side. We have multi-rotor arrays. We've seen this in China where they have one foundation but 2 turbines attached to it, so it branches out. We have offshore vertical axis wind turbines, a personal desire of mine. Because the vertical axis has the machinery at the bottom, it's easier to service. It's able to handle higher storm conditions. It doesn't have to face the wind. There's a lot of advantages, but they don't operate as effectively as horizontal axis wind turbines, which is why we don't see a lot of them. Superconducting generators, obviously the reduction in losses through transmission and through the generation. We have bladeless wind turbines, basically giant columns that just start shaking, and as they shake, they generate some kind of electricity. None of these have been put into production. These are all either test or only theoretical at the moment. And that, ladies and jelly spoons, is my presentation. I hope it was useful. Thank you very much.
Yo, Gareth, we gave you a challenge to pack so much into 15 minutes, and you've done a great job of that. And I can just imagine that each of those points that you've raised could almost be a talk all by itself. Incredible. It reminds me that in engineering, we just don't hope for favorable winds, we model them. But what I've seen also, it's just all these challenges about noise and birds and degrading, that challenge becomes a design thing, not only a modeling thing, and all the work that goes into design it even better and more efficiently. That has been absolutely incredible. Thank you for that. The same wind blows on us all. The difference is how we set our sails. And from a different direction and a different approach around wind energy, we're going to ask Professor Dirk van Walt, who's the CEO of Rock Conservation Tech, to come and talk to us. Oh, no, why did I say professor? Sorry. Dirk is the CEO of Rock Conservation Tech. He's a registered professional engineer with over 20 years experience in control and instrumentation. He focuses on integrating AI, artificial intelligence, with functional safety principles to address the environmental risks in the renewable energy and the developments thereof. His work supports the deployment of IdentiFlight, that he's going to show us today, an advanced monitoring and mitigating system. He works closely with developers, regulators, and conservation organizations to deliver data-driven practical solutions that align sustainable energy expansion with the protection of vulnerable bird species and ecosystems. I must say, every time I talk to anyone about wind energy, the first question they ask is, what about the birds? And I'm very excited that Dirk is going to answer those questions for us today. With that, Dirk is going to talk about wind energy that soars without harm. Wind energy that soars without harm. Dirk van Walt. Thank you, Dirk.
Yes, like in the process industry, everybody reads the HAZOP and safety briefings, but unfortunately, none of the birds attend the EIA of when the wind farm is being built. So it's why we need to help them. So yeah, my talk is going to put out just to position ourselves around automated shutdown on demand, how it works, and what makes a successful automated shutdown on demand system. I think it's a technology that has been around for quite some time.
Dirk, I can't hear you. I'm not sure if anyone else have. All of a sudden, it just popped out.
Sorry, can you hear me?
I still can't hear you.
Is it better?
Oh, I see a thumbs up, so someone else can hear you. Then it's on my side.
Cool. Thanks. Yeah, so I think first of all, positioning automated shutdown on demand. How do we protect the birds? So first of all, there's always people ask us, can we not relocate or move them? That's very frowned upon. And then the second step, or the first step really, is positioning that you're not in high risk areas. But unfortunately, most of our wind resources and where our birds love to nest is is closely related. So then the question around deterring the bird. So can you visually deter it with painted blades? It's semi-successful, or auditory deterrence, that you scare the bird away when it gets there. But we also don't like doing that, as you want to keep the bird in its environment and not chase it away. It defies the purpose a bit. What we do a lot in South Africa for the last 5 years since we've started is we've monitored very well. So the wind farms, they do carcass searching, counting birds, but that's we're just seeing the result of not preventing anything. So then we get to how do we really protect the birds, and that's by avoiding a collision. And you can only really avoid a collision is by stopping the turbine, as the bird doesn't read our notices and look at around it. It's busy hunting. We need to stop a turbine to ensure that we've got successful automated shutdown. So I hope through this presentation I will be able to give you a good overview and bring a bit of the functional safety into how we used to protect humans. We also can protect our wildlife. So I think as we start, the most important thing is it is just a physics sum. A turbine typically takes 60 seconds to stop. We need to detect a bird before it gets to the time we need to stop the turbine. So we need to detect a bird at, say, 1 kilometer away. Then we identify the bird. Say, is this a bird we need to protect? If it's a bird we need to protect and it's on its way to the turbine, we need to switch down that turbine. And that's really the only way you can have a successful automated shutdown on demand system, is by stopping the turbine. If we detect the bird too late and stop the turbine too late, it is there's a high probability that the turbine blades will still be spinning, and you can end up with a fatality on that species. And I think that's the when I started, this is quite a simple principle for engineering problem to solve. So why don't we do it more? So what we do is essentially with our system that sits on a mountain or on away from the turbines, is we look out at the turbines and then track the birds as they fly through the wind farm. And then as it goes into a rotor swept area of a certain turbine, you stop that turbine. It's all easier said than done, as no detection can end up in a fatality. Late detection can also end up in a fatality, but so we want early detection and quick action to be taken. Typically, and this gets done through just essentially these 4 steps that you need to take to ensure that you are successful in protecting our birds. So first of all, the validation. We need to design the system right. In my engineering career, I've seen it many a time, is we need to understand the problem and design the solution. We can't just install something and hope it works. So typical things like the time that the turbine takes to stop, well, your rotor diameters, the hub heights, the layout of the land, all of those are the inputs to the design. Along with that, we look at what birds do we want to protect. So typically our soaring eagles and vultures, they fly around at 10 meters a second. And that's what we use. So we simple maths, 10 meters a second, rotor takes 60 seconds to stop. So at 600 meters, we already need to start to stop the turbine to ensure the turbine is at 1 RPM by the time the bird gets to the turbine. So then we get to validation criteria. So now we get to how do we do it? And that's essentially camera lenses. You need to have proper cameras, proper resolution, proper optics, along with it needs to be able to work in the windy, dusty area out in the field. And then how do you design it? Where do you place it? Is it on the turbine, off the turbine? And how does it look? I always tell people it's like if you go to the Kruger and you've got 2 people there, one with their iPhone taking pictures of the lion and one with one of those white Canon lenses. if you use the wide Canon lens, it is a more expensive lens, but you definitely get a lot better image of that lion. So the technology is not just the AI or the system, but it's all the way from your field sensors and equipment that you need to look at. Then you need to look out, how do you design this? So we want to design to ensure that we have got fully covered turbines. So what a fully covered turbine means is that we can see 95% of the shutdown cylinder of each turbine with a unit. As you can see, a lot of these units, one unit can cover multiple turbines, but if you're not going through these design steps, you can end up with turbines that's partially covered or not covered due to terrain effects or just the range that you need to detect the birds at. So essentially, you need to have a properly designed system. And then you get to a system that's installed, and now you're looking at pictures, because these are visual systems mostly, and we are processing petabytes of data. Anyone that's been as a videographer or take in pictures, these things are megabytes and gigabytes of data that you need to work with. So that now gets into how do you see the data. So as you can see, here's some example images of on the identified system of this is a fish eagle. You can see the system ID'd it as a fish eagle. And this was taken at 1,200 meters away. And I always tell people to look at the image. If you can ID the bird, the system can ID the bird, because all of these AI systems are just a looking at the picture and doing processing that. There's no magic in it. So as soon as you've detected the bird, then you need to take action. And that's where you get into how long does the turbine take to stop? How do you integrate with the SCADA? As soon as you integrate with the client SCADA, there's a lot of questions on data security, cyber security. How do we, because it's same as with sills. As soon as you're on the control system and you want to trip the plant, everybody is very, very reluctant to do that. So, and then as soon as we trip the plant, people, production is always asking, but how much power am I going to lose? And that's exactly why we say we should look at ensuring that you are shutting down species specific, as we want to protect our vulnerable and endangered species. We need to ensure that we only stop for them. We are not going to stop for the crow that's flying around there as well. And looking at our data and feedback from clients is we are currently with over 500 units installed, seeing production losses of less than 1%, at 0.7% on average on these wind farms. So really it does impact, but very little. But the flip side of that is if you're not doing this per species the right way, you can end up curtailing turbines from 5 to 10% of time, because we are in nature. There is a lot of other birds that's also flying around there. So that's always the other side of the coin, is we want to stop, make sure we're protecting our birds, but we also want to make electricity that we can watch the rugby. Just a little bit on around the AI. That's always AI. People, it's got a bit of magic, but it essentially learns like all of us. We need to give it a lot of images of our birds we want to protect, ensuring we cover adult, juveniles, males, females. And if we've got a proper system and a proper design system, we keep the humans in the loop with regular testing and ensuring validation from humans. We can build AI models that can very easily distinguish between species that look very common. If you look at here, we can easily tell between a honey buzzard and a common buzzard. That for even human birders can know that that's quite a challenge. So in South Africa already, we've got over 30 species, and as we're going along, we're adding more species to the list that we can ID and protect for. And yeah, I think that gives you a quick and dirty overview of how does automated shutdown on demand work, and how we can really protect our natural resources. And all South Africans love going into the veld and enjoying it. And we can generate power and still keep our wonderful birds alive. So thank you very much.
Wow, Dirk, that was absolutely fascinating. You didn't even chase the wind. You actually categorized the wind, you categorized the birds, you categorized all the aspects around that. Very interesting. What a breath of fresh air looking at the other side of the engineering. Before we go to the next phase, everyone just please ask your questions on the Q&A. Or I just need to mute here. Please remember to ask your questions. We are soon going into our Q&A, where we would like the presenters to answer some of the questions. So today we have shown that wind energy is much more than taller turbines. It's a place where there's different approaches, different disciplines involved, different technologies, and it all comes together. And as South Africa expands its renewable energy portfolio, innovation will not only be measured by how much electricity we generate, but also how intelligently and responsibly we do it. Thank you for our speakers to share your expertise and your passion with us. All the preparation prior, we really appreciate that. Thank you for each and every one of you who have joined us, and please stay on for the Q&A session as well. We would love to see you at our next webinar as well. We have posted the next webinar into the chat box. Remember, there will be the YouTube videos for the webinar and for the Q&A session that you can expect over the next month. And in 2 months' time, we're going to see you again.